Welcome to my talk. My name is Fabian Kuhn and this is joint work with Mohsen Ghaffari from ETH Zurich. Our paper is on distributed graph algorithms and more specifically on distributed graph coloring. I will start by giving you some context. Let's start with the model of computation that we are using. We are considering graph problems in a very classic distributed message passing model where we have a network which is modeled as an undirected graph. We typically assume that the network, and thus the graph, has n nodes and that each node is equipped with a unique O of log n bit identifier. Communication happens in synchronous rounds. In each round, each network node can do some arbitrary local computation. Afterwards, each node can send a message to each of its neighbors, and by the end of the round, each node also receives the messages sent to it by its neighbors. The time complexity of an algorithm is measured by the total number of such communication rounds. There are two standard variants of this model that are widely studied in the literature. In the local model, the amount of information that can be exchanged in a single round is unrestricted, and in the congest model, messages have to consist of at most O of log n bits. In the distributed coloring problem, our goal is to compute a vertex coloring of the network graph on which we run the distributed algorithm. Typically, we assume that at the beginning, each node only knows its own identifier and possibly something about its direct neighbors, but nothing else about the topology. In each communication round, the individual knowledge of each node about the graph grows by one hop. And after the last round, each node still has some restricted, pretty local view of the graph, and based on this information, every node has to compute its output. At the end of a distributed coloring algorithm, every node must know its own color in the computed vertex coloring. In the standard variant of the distributed coloring problem, the objective is to compute a proper coloring with delta plus 1 colors, where delta is the maximum degree of the graph. Note that this is what can be achieved by a simple sequential greedy algorithm. A bit more generally, people also study the degree plus 1 list coloring problem, where every node is initially given a list with degree of the node plus 1 colors, and it has to pick a color from that list. I don't want to say much about why we should care about distributed coloring. Let me just mention that it is a simple but prototypical problem to study distributed symmetry breaking in graphs. Coloring is also used as a subroutine in many higher level algorithms, and techniques developed in the context of distributed coloring often also find applications in other distributed or parallel graph algorithms. Before getting to our new contribution, I will spend some time talking about previous work on distributed delta plus 1 coloring algorithms. Because our paper is on deterministic algorithms for the problem, I start with what we know on deterministic distributed coloring algorithms. First, there is a long line of research that tries to optimize the complexity of a problem as a function of delta while trying to keep the dependency on the number of nodes n as minimal as possible. Note that by a classic result of lineal, it is known that log star n rounds are necessary to compute the delta plus 1 coloring, even in graphs of degree 2. Currently, the best known algorithms as a function of delta solve the delta plus 1 coloring problem in time roughly square root of delta. As a function of n alone, the best classic deterministic delta plus 1 coloring algorithm has a time complexity of 2 to the power of square root log n. Note that while this is subpolynomial, it is still exponentially slower than a polylogarithmic running time. While getting a fast deterministic distributed coloring algorithm has been a challenging problem, there are basic and fast randomized distributed delta plus 1 coloring algorithms. There are different simple ways to compute such a coloring in only O of log n rounds. In recent years, there has also been work on faster and more involved randomized coloring algorithms. All those algorithms use a method that is now known as graph shattering. They first apply some randomized algorithm to color a large part of the graph, such that at the end of this randomized algorithm, all the connected components of the remaining uncolored parts have size at most polylogarithmic in n. Those remaining components are then solved by some deterministic algorithm. The 2 to the order of square root log n terms in all those bounds here therefore all come from applying the deterministic algorithm mentioned on the left to graphs of polylogarithmic in n size. In the last couple of years, there were finally also some improvements on the deterministic complexity of coloring as a function of n. The big breakthrough came with the algorithm of Mohsen and Ghaffari and the slightly improved version of their algorithm by Ghaffari, Grunow, and Mohsen. They showed that the delta plus 1 coloring problem, and in fact also many other distributed graph problems, can be solved deterministically in only polylogarithmic time. Because of the way in which all the fast randomized algorithms work, this also directly improved the time complexity of the best randomized coloring algorithm from exponential in square root log n to polylog n. So far, the fastest deterministic distributed coloring algorithms are based on a structure that is known as network decomposition and that has been introduced in the late 1980s. A network decomposition is a partition of a graph into clusters of small diameter, together with the proper coloring of the graph induced by the clusters, with a small number of colors. Think of the cluster diameter and the number of cluster colors both to be log n or polylogarithmic in n. Given a network decomposition, there is a simple brute force way to solve delta plus 1 coloring and also many other graph problems. One can iterate over the cluster colors and then solve the problem in the different clusters of a given color by learning the topology of the cluster in time equal to the cluster diameter. Until a couple of years ago, the best deterministic algorithm to compute the network decomposition had a time complexity exponential in square root log n. And this is also the reason why the best deterministic time complexity for computing a delta plus 1 coloring was exponential in square root log n. The breakthrough result of Mohsen and Ghaffari was actually obtained by finding a deterministic network decomposition algorithm with only polylogarithmic round complexity. While the result established that delta plus 1 coloring and many other distributed graph problems can be solved deterministically in polylogarithmic time, the method is quite brute force and it does solve the problem in a somewhat indirect way. The main result of our paper is a deterministic distributed algorithm that solves delta plus 1 coloring faster and much more directly than the algorithm based on network decomposition. We show that the more general degree plus 1 list coloring problem can be solved in order log square delta times log n rounds. In fact, as long as the color lists of the nodes are composed of colors from a range that is at most polynomially large in delta, the same result can even be obtained in the congest model, that is, with messages of at most O of log n bits. As a direct corollary of our algorithm, we also obtain a faster randomized distributed delta plus 1 coloring algorithm. Here we improve the time complexity from log n to the power of 5 to log n to the power of 3. In combination with a very recent new randomized coloring algorithm, the same is now even true in the congest model. In addition, we get some additional deterministic coloring results for related problems. We show that in graphs of arboricity A 2 plus epsilon times A coloring can be computed in time log to the 3 of A times log n, and for delta at least 3, and as long as the graph is not a delta plus 1 clique, one can deterministically compute the delta coloring in time order log square delta times log squared n. In the remainder of my talk, I want to give some insight into how the algorithm to prove our main result works. We start this by an observation one can make by looking at some previous work on distributed deterministic graph algorithms. While deterministically obtaining combinatorial solutions that require symmetry breaking can be challenging, very often it is much easier to compute solutions to some fractional relaxation of a given problem. A somewhat natural approach to obtaining deterministic distributed algorithms for symmetry breaking problem is therefore the following. One first solves some fractional relaxation to the problem, and one then deterministically rounds the fractional solution to an integral one. The potential of this method has in particular been demonstrated in some recent deterministic distributed algorithms for the maximal matching problem in graphs and in low-rank hypergraphs. The algorithms of the two papers mentioned here provide the fastest known deterministic distributed algorithm for the maximal matching problem in graphs, and the first polylogarithmic time deterministic distributed algorithm for the 2 delta minus 1 edge coloring problem. The idea of deterministically rounding a fractional solution has also been used implicitly by all the deterministic distributed maximal matching algorithms, and it has recently also been applied in the context of approximating the minimum dominating set problem. In order to apply the idea of deterministically rounding a fractional solution to the distributed coloring problem, there are two main challenges that we need to deal with. First, we need to have the right fractional relaxation of the coloring problem or of some other problem that can be used to solve coloring. Based on our experience, it is most promising if we have a fractional problem for which rounding at least becomes simple and local if we can use randomization. Also, once we have an appropriate problem, we of course have to come up with an efficient deterministic distributed rounding scheme. At the core of the fractional relaxation that we consider is the following simple randomized coloring step. Assume that every node just independently and randomly chooses one of its available colors. That is, it chooses one of the colors that is in its list, and also a color that has not been already assigned to a neighboring node, in case we start with a partial proper coloring of the graph. Let's look at some properties of this simple randomized coloring step. For this, assume that every node V has at least degree of V many colors available. If we already have a partial coloring of the graph, just assume that we only run the algorithm on the uncolored part of the graph and think of the degree of V as the number of uncolored neighbors of V. For any two neighbors U and V, the probability that U and V randomly choose the same color is at most 1 divided by the maximum of the 2 degrees of U and V. To see this, just fix the color chosen by the node of the smaller degree and consider the conditional probability of the other node choosing the same color. If we define a random variable x as the number of edges for which both endpoints randomly choose the same color, then we can upper bound the expectation of x by the sum over all edges of 1 divided by the maximum degree of the two nodes of the edge, and this can be upper bounded by n divided by 2. Therefore, in expectation, every node has at most one monochromatic edge. We can now define the fractional problem that we are considering. We just assign a probability distribution over colors to each node. We call this a fractional color assignment. And we define the cost of such a fractional color assignment as the expected number of monochromatic edges if every node chooses a color independently according to its distribution over colors. Note that by linearity of expectation, we can separate the cost of a fractional solution into a sum of individual edge costs, where the cost of an edge only depends on the color distribution on its two nodes. By the observation from the previous slide, we know that if each node has a uniform distribution over at least degree of the node many colors, then the total cost is at most n divided by 2. Note that if we have an actual assignment of a single color to each node such that there are at most O of n monochromatic edges, then the subgraph induced by the monochromatic edges has constant average degree and therefore an independent set of size theta of n. If we have such a color assignment, then we can also efficiently find such an independent set and then permanently assign the nodes of this independent set their chosen color. In this way, we can color a constant fraction of all the nodes. Our main task, therefore, is to find an integral color assignment of total cost O of n, with O of n monochromatic edges. We will achieve this by rounding a given fractional color assignment in a gradual fashion. For convenience, we will assume that all the fractional values in the fractional color assignments are inverse powers of 2. For a non-negative integer k, we say that the fractional color assignment is 1 over 2 to the k integral if the smallest fractional value of a color in a color assignment to a node is not smaller than 2 to the minus k. Note that for k equals log base 2 of delta, a 1 over 2 to the k integral color assignment with total cost O of n can be computed without communication in a simple way. Instead of starting with a uniform distribution over colors, we just start with an almost uniform distribution in order to make sure that all fractional values are inverse powers of 2. Let's now look at how to deterministically round a fractional color assignment. We start with a basic algorithm that is still too slow. Assume that we are given a proper seq coloring of the nodes of our graph, and that we are given a 2 to the minus k integral fractional color assignment. We claim that we can then obtain a 2 to the minus k minus 1 integral fractional color assignment with equal or better total cost in C rounds. The idea of the algorithm is very simple. We iterate over the C color classes, and when considering the nodes of a specific color, we compute a new 2 to the minus k minus 1 integral assignment to those nodes in parallel. To see how we can do this, let's consider an example. Consider some node V with a 2 to the minus 4 integral fractional color assignment. In order to turn this color assignment into the 2 to the minus 3 integral color assignment, we only need to change the fractional values that are equal to 2 to the minus 4. Note that because the sum of all fractional values is equal to 1, the number of 2 to the minus 4 values must be even. In order to keep the sum equal to 1, we can therefore round half of the 2 to the minus 4 values up to 2 to the minus 3, and we can round down the other half of those values to 0. We do this in such a way that the total cost of the edges of node V does not increase. Note that we can do this because if we choose the colors for which we round up randomly, then the expected cost does not change. In fact, we can just round up the colors for which the sum of the fractional values among the neighbors of V is minimal. Note also that because the cost of an edge only depends on the fractional assignment of its endpoints, we can do this rounding in parallel as long as we do not round the values of two neighbors at the same time. Note that while the rounding of the last slide is without loss, it is potentially very slow, even if a reasonably good proper coloring of the graph is given. As we will discuss next, we can however significantly speed up the rounding if we allow a small increase in total cost. For this, we use a so-called defective coloring. It is known that in an edge-weighted graph, for every positive parameter epsilon, it is possible to efficiently compute the coloring with order 1 over epsilon squared colors, such that for every node V, at most an epsilon fraction of the weight of V's edges is on monochromatic edges. Such a coloring can be computed in only log star n time. Actually, if we spend log star n time once at the beginning to compute the delta squared coloring of the graph, then such a defective coloring can even be computed in time log star delta. Let's illustrate this at an example. Consider some node V with its neighbors. For the example, we assume that the value of epsilon is 0.1. The total weight of V's edges is 2.65. We want the coloring of the nodes such that at most 10% of this weight is on monochromatic edges. Here is such a coloring. The node V is colored red and the total weight of all edges connecting V to other red nodes is 0.25. For our rounding algorithm, we now proceed as follows. We first compute a defective coloring for an appropriate value of epsilon and where the weight of the edges are the current edge costs. We then ignore the monochromatic edges and consider the graph that is induced by all the other edges. For this graph, we have a proper coloring with order 1 over epsilon squared colors. Also, by the property of the defective coloring, a 1 minus epsilon fraction of the total edge cost is on the edges of this graph. We then run the rounding algorithm from the previous slide on this graph, which we can now do in only 1 over epsilon squared rounds. Here is now where we really use the fact that we increase the fractional values of the color assignment by at most a factor 2. Because of this, the cost of the monochromatic edges, which we are not considering during the rounding step, can grow by at most a factor 4. The total cost therefore grows by at most a factor 1 plus order epsilon. In order to keep the total cost small enough over all rounding steps, we choose epsilon as 1 divided by theta of log delta. As we saw, we can implement one rounding step in order 1 over epsilon squared and thus in log squared delta rounds. As discussed, the total cost of the edges that are properly colored by the defective coloring does not increase, and the total cost of the monochromatic edges increases by at most a factor 4. The overall cost therefore grows by a factor at most 1 plus order 1 over log delta. Since we start with fractional values of order 1 over delta, we need O of log delta rounding steps. The overall time for the rounding is therefore log to the 3 delta, and at the end, the total cost grows by at most a constant factor and is therefore still O of n. We can therefore properly color a constant fraction of the nodes. Let's conclude with a brief summary. As discussed, we can color a constant fraction of the nodes in log to the 3 delta rounds, and we can therefore color the whole graph in order log to the 3 delta times log n rounds. This is by a log delta factor slower than what I claimed is our main theorem. In order to speed this up, one has to replace the defective coloring algorithm by a more involved algorithm with somewhat different guarantees. all our remaining results are obtained by adapting the same basic rounding method and by combining it with some additional ideas. This concludes my talk, and I thank you for your attention.